we now see the possibility of having higher level NPC based converters. Okay. Now, often and it has been proposed in the research community that we can go from a 2 level to a in a conventional NPC we have gone to 3 level NPC. Why do not we go for a higher level NPC? Okay. Now, why do we want to go for a higher level NPC? Because it will improve the waveform quality. Okay. And of course, it will improve the inverter's voltage rating or the converter's voltage rating. Now, if you go with a 5 level NPC, if you see the space vector diagram, then you can immediately see what is the advantage of having a 5 level space vector diagram or a 5 level NPC. You can see here in the diagram. So, you have a space vector diagram for a 2 level converter, for a 3 level converter and for a 5 level converter. And you can see that in a 5 level converter, the space vector diagram, the space vectors in the space vector diagram, they are getting closer and closer to each other, they are becoming more dense. So, that the instantaneous error between the reference vector and the actual vectors which we are switching, that instantaneous error is reducing. And if the instantaneous error reduces, we are approaching closer and closer to the sine wave, desirable sine wave. So, that is why a 5 level space vector diagram or a 5 level NPC will be better in terms of waveform quality than a 3 level NPC. Okay. So, how does a 5 level NPC look like? So, you can see it here in this circuit, one phase is shown. So, you can see that you have like 8 switches here, okay, for the 5 levels, and there are also clamping diodes, but these clamping diodes, there are several clamping diodes here. So, let us see a little bit about this one, the circuit. So, you have this VD voltage here and the minus VD voltage and the 0 point here, okay, like a conventional 3 level NPC. But now, you have also like 4 capacitors here, and the voltages at these points are, all the capacitors have equal voltages. So, that this is 0, this is VD by 2, this is VD, and then minus VD by 2 and minus VD. So, the whole DC bus voltage is split into 4 equal parts across all the capacitors. Okay. So, in this converter, suppose we want to get the VD voltage, that is the voltage of the pole voltage with respect to this 0 point. If I want to get VD, then I will turn on 1, 2, 3, 4, all the 4 switches here. On the other hand, if I want to get VD by 2 voltage plus VD by 2 voltage, you can, what we can do is we can turn off this one, turn off this switch and turn on this switch, okay, right. We will turn off this switch and turn on this switch. So, if we do that, then what happens? The current will flow from this way. So, let me so for VD voltage, we will turn on these 4 switches for VD voltage. Okay. That means point the voltage of A with respect to O, then we will turn on these 4 switches. Okay. And then we will in order to get VD by 2 voltage, what we will do? In order to get VD by 2, this switch is turned off and this switch is turned on. So, now we have these 4 switches conducting. So, if the current direction is positive in this way, if the current direction is positive, then the current will flow like this here, right. The current will flow like this. On the other hand, if the current direction is negative, then the current will flow like this. Okay. Okay, like this. So, this is how we by these 4 switches we will be able to get a Vd by 2 voltage, right. In a similar way, if we want to get the Vd voltage, then what can we do? If we want to get if we want to get a 0 voltage, what can we do? We can turn on this 4 switches here. Okay. So, and so this point will be accessed via this. So, either the current will flow like this or the current will flow like this. Okay. So, if you go on analyzing this way, you will see that this in this particular NPC or the 5 level NPC, how we can get the 5 levels of voltage, that is Vd, Vd by 2, 0, minus Vd by 2 and minus Vd in the pole voltage. Okay. This particular converter, although is attractive, but there is a one drawback, and the capacitor balancing, because now we have 4 capacitors here, and balancing these 4 capacitors is a major challenge for this type of a converter, and so it has not been much popular. So, 3 level NPC is very popular, however, 5 level or higher level of NPCs are not so popular. Okay. The capacitor voltage balancing is a major issue, but if some of you are interested in exploring further, we will add references where you can study this material. Okay. Then we will talk about something like a TNPC. Okay. So, this is another, so this is another type of NPC, where this has been proposed more recently. Okay. So, here what happens is circuit is like what I have shown on this circuit diagram here. Now, if you see here, the in TNPC we have one upper switch, one lower switch and 2 switches to access the 0 point here. Okay. So, this point is like plotted here. Okay. So, this is what we have. Now, in this case, the difference of this is the difference of this TNPC from the conventional NPC is that we have only one switch here, okay, and there are no clamping diodes. Instead of the clamping diodes, okay, here there are no clamping diodes. Instead of the clamping diode, we have these 2 switches. Okay. Now, remember that. So, what are the, so remember that what are the ratings of these switches here? So, this switch, the upper switch is rated for the full DC bus voltage, and the same is applied for the lower switch also, because if this switch is off and this switch is turned on, then the whole voltage will come here. So, this switch has to block the full DC bus. Okay. So, the voltage rating of this switch as well as this switch is Vd or the total DC bus, whereas the voltage rating of this switch here is half the DC link voltage. Okay. Now, this switch is a 4 quadrant switch. So, which means that this switch has to block both plus and minus, I mean positive and negative voltage, right, and the current through this switch here should be bidirectional. You can see that if S3 and D4 are conducting, the current will flow like this here. If S4 and D3 are conducting, current will flow like here. So, this switch is a bidirectional current switch. It can also block bidirectional voltage. So, if I turn on S1, the plus voltage will come here, okay. The plus voltage will come here, and if I turn off S3, then this device will not conduct. Okay. On the other hand, if I turn on S2, then the minus voltage will come here. So, therefore, we can say that this switch is a 4 quadrant switch, okay, rated for half the DC link voltage, but switches S1 and S2 are rated for the full DC link voltage. Now, let us see how does this circuit operate. So, if I want to get the positive voltage and suppose the current which is going out is greater than 0, then I have this, this is the switch, S1 is the switch which is conducting. If I want to get the 0 voltage, then the red path here is how the switches will be conducting, and on the other hand, if I want to get the minus Vd by 2, this diode D2 will be conducting, that is what it is shown here. Okay. So, this is for the condition when the pole current is greater than 0. What will happen if I0 is less than 0? In that case, for Vd by 2 voltage, the diode D1 will be conducting, and for the 0 voltage, these S4 and D3 will be conducting, and for the negative voltage, S2 will be conducting. Okay. So, these are the different switching states of or different configurations of the switch for these 3 states. Okay. So, therefore, comparing this T type NPC or TNPC, we see that compared to a conventional 3 level NPC, we have less number of switches here. Why? Because in conventional NPC there are 10 switches, there are 4 transistors, 4 antiparallel diodes and 2 clamping diodes, right. But in this topology, in this TNPC topology, there are 8 switches. Okay. Of course, these 8 switches have different voltage ratings, but overall it has been reported that this operation it increases the converter efficiency. Okay. You can easily understand, like when you have the plus and the minus states, then only one device is conducting in this topology, whereas in a 3 level NPC during the plus and minus states 2 switches are conducting. So, therefore, it has been reported that TNPC actually increases the converter efficiency. We will again not go much in details about the operation of TNPC, and interested viewers are requested to see additional reference material. The other NPC which is also somewhat popular is the active NPC. So, active NPC was also proposed in the around 2000 or 2001 maybe. So, in active NPC what happens is, we know from our operation of conventional 3 level NPC that there is an uneven loss distribution in all these 4 switches. So, among all these 4 switches there is an uneven loss distribution. Okay. Suppose we are working with a modulation index close to 1 and unity power factor, then we have seen that the outer devices will have more losses. Okay. Why? suppose you can see, suppose the VAO voltage is like this and S1 will be therefore switching like this and S2 will be fully clamped, right. And so, if it is like unity power factor, the current waveform is also very closely following the fundamental of the pole voltage waveform. And so, we see that S1 has both conduction as well as switching losses, whereas S2 have only conduction loss. So, with a reasonably good switching frequency, S1 will have more losses. Similarly, S4 will have more losses. So, in order to, so then what happens is, over time the temperature of S1 and S4 becomes more than the temperature of S2 and S3. So, active NPC was proposed in order to equalize the loss distribution. Okay. So, what happens in an active NPC? The circuit topology is this side remains the same, whereas here we have two switches. Here we have two additional switches, and these two switches are used in equalizing the losses. Okay. Now, again so here one thing we observe that the 0 state, okay, the 0 state can be like this combination. So, the current can flow through the upper path or current can flow through the lower path for the 0 state. Okay. How, for example, I want to access the 0 state, I will turn on, if I turn on S2 and S5 for the 0 state, then if the current is going out, so the current can flow either through D5 and S2 if the current is like this way, okay. And if the current is the other way, if the current is the other way, that is coming in, then D2 and S5 can be conducting. Okay. So, if I turn on S5 and S2 simultaneously, then I can fully allow the current to flow through the upper path. Okay. Both positive and negative direction of current can be allowed to flow through the upper path. So, therefore, the entire loss can take place through to the in the upper two switches. Okay. On the other hand, if I turn on S3 and S4, S3 and S6 for example. So, let me again rub this off. So, if I want the current to flow through the lower path only for the 0 state, then I will turn on S3 and S6. Okay. So, now if the current is like this in this way, then S3 and D6 will conduct like here. On the other hand, if the current is like this way, then S6 and D3 will conduct. So, whether the current is positive or negative, I can force the current to flow through this lower path only, okay, and I can fully cut off the upper path. So, this is the one of the main differences of NPC and active NPC. Okay. I can force the current to go through the upper path or the lower path. Okay. Now, another thing that is done here is that when the upper path is being used, this lower switch S4 can be made on or off. Similarly, when the these two switches are turned on, this S1 can be made on or off. Why do we do that? Because next time after the 0 state, if I want to switch on the plus state or the minus state, then the switching losses can be minimized, or I can say the switching losses can be transferred from the outer device to the inner devices. Okay. Now, the full analysis and explanation of this again I will not cover in this course, and we will put a reference for this one, because we do not means the full analysis will take a substantial time. So, the full analysis of this can be seen in the references. The main advantage of using an active NPC is that it is useful in equalizing the losses across the converters. So, the temperature rise distribution is more uniform across all the switches in active NPC. So, with this we conclude the discussion on neutral point clamped converter. So, we started with the basic topology of NPC, then we talked about the space vector diagram, and then we also talked about carrier based PWM implementation. We also talked about capacitor balancing, and we briefly touched upon some other topologies of NPC which you can explore further.